This is correlation coefficient. The purpose of correlation coefficient is to determine the degree of linearity of the data. This is the equation for correlation coefficient. The top of the equation determines the direction of the correlation. The bottom of the equation determines the strength of the correlation. The first thing when doing correlation coefficient is writing out your data. After you write out your data, it's important to plot it on a scattergram. Scattergrams typically look like this. Once you have your scatter plot, it's important to find the averages for both the y values and the x values. In this case, with our data, the x mean is 50 and the y mean is 30.5. Then you must graph these x bar and y bar lines on the scatter plot. The point at which they meet is known as x bar, y bar.
After finding the point x bar, y bar, you then have to find the orientation of each data point in relation to the x bar, y bar lines. For instance, any data point on this side of x bar and on this side of y bar will be positive, positive. This side will be positive, negative. This will be negative, negative, and this will be negative, positive. Stop. After you have found the orientation of the individual data points, you must find the actual orientation of all the data. To do this, you must subtract x bar from the x value of the data point. For example, x minus x bar. This x value may represent any x value from any of the data points on the graph. This must be repeated with the y value of the data point y bar. So for instance, y minus y bar. The next step is to multiply the individual orientations of the x and y values of the points together to find the overall orientation of the data point. After this is done, one must find the average orientation for all of the data points by adding up all of the numbers and dividing by the number of numbers.
Having a large standard deviation means that the data is broadly spread around the mean. A small standard deviation means that the data is consolidated around the mean. If the data has a small standard deviation, then the equation will have a small denominator, meaning the value will become closer to 1 or negative 1, increasing the correlation. This step is represented by the SXSY step of the equation. According to our data, we found that the correlation was 0.91. This means that it is a strong positive correlation. The variables for our data were number of trees and depth of snow. Because we found a strong positive correlation, this means that there is a strong correlation between trees, number of trees, and depth of snow.
Chi-squared is used to test how far your data is from true independence. The step to finding chi-squared is identifying your null and alternative hypothesis. Your null hypothesis is that height and SAT scores are independent of each other, and your alternative hypothesis is that height and SAT scores are dependent on each other.
So the second step is to find the mean of the x and y variables. So in this case, we find the mean of height and SAT score. So here is the observed frequency table, and so we found that the mean of the height was 5 feet 5 inches, and so we're going to find the values below this number and above this number. And we did the same for SAT score, and we found the average to be 1,500. So we're going to do scores below and above that number too, to find our observed frequency. And we do this because we want to categorize them, we want to unbiasedly categorize them.
Chi-squared equation where FO equals observed frequencies and FE equals expected frequencies.
Alright, so step 3 is we are going to establish what our frequencies would look like if they were fully independent. And so this is the frequency of the expected values. And so we look back at our observed frequency table and we find the probability of less than 5 foot 5 inches and less than 1500. So to do this, we would add 20 plus 18 to get 38 and divide it by 56 to equal 21.7. And then, so you're going to do this for basically all your values. So, for example, the next one would be greater than 5 foot 5 inches and less than 1500, and you would get a value. And then so on and so forth. And these are going to be your expected values. We're going to next take our observed frequencies and subtract it from our expected values and square this. And this is because we don't want our values to cancel each other out. And then next we're going to divide it by the expected value. And this tells us how far our value is from independence. Alright, so next we're going to do, going back to our observed frequency table, we found 20, and so then we subtract it from our expected value, which is 21.7, and then we're going to square that to get 2.89, and then divide it by the expected value. Overall chi-squared value, you're going to need to find the sum of all of these values. So in the previous slide, we just did an example calculation for this point right here. So next, we're going to do it for all the 3 other points corresponding to their expected value, and add that together to get your chi-squared value.
You have to solve for your degrees of freedom. So you do this by figuring out how many columns you have, which is 2, minus 1, which equals 1. Then you take how many rows you have, which is 2, minus 1, which equals 1. And you take these two numbers and multiply them together, which equals 1, and that gives you your degrees of freedom. You plug into the chi-squared equation and get your chi-squared value. Calculating for chi-squared, you take that value and apply it to the critical values table. Chi-squared value of 0.967 is lower than the critical values at the 10, 5, and 1% level. We can tell that our data is independent of each other.